This is the next video in the chapter on chemical bonding and molecular geometry. We just finished learning about ionic compounds and how they're actually a regular repeating network of cations and anions and not just a molecule. So let's talk about what those compounds look and act like. So ionic compounds have certain properties in common with each other. So they can be identified by their characteristic properties. And we're going to put a line down the middle of the page here so we can talk about other properties on the other side. So some properties of ionic compounds include being crystalline, such as when you look at a table salt under the microscope and you can see that it contains small, regularly repeating squares. They are brittle, meaning that they shatter easily. They tend to have pretty high melting points and boiling points. And they're soluble in water. And when they dissolve in water, they separate back into their ionic components. Oops, hold on. Spelled soluble wrong. So they're soluble in water. They separate into their ionic components. And when they do so, that solution becomes conductive. So the actual salts, like sodium chloride by themselves, are not conductive, but when they're dissolved in water, then they become, the solutions are conducting. So these properties of ionic compounds, crystalline, brittle, high melting and boiling point, and soluble, these are very different than the properties of the individual atoms and elements that make them up. And this should sound familiar. We talked about this when we learned about the definition of a molecule, of a compound, and the definition of an atom and of an element. Is that when we rearrange atoms in a chemical reaction to form new elements, to form new compounds rather, the compounds have very different properties than the elements that make them up. So these ionic compound properties are very different from the neutral atoms that they are composed of. For example, we can return to our favorite table salt. We can react sodium and chlorine to form sodium chloride. But sodium is a gray colored, very soft metal, which is very dissimilar from chlorine, which is yellow in color and also happens to be a toxic gas. So the two elements we're mixing together are super different. One of them tends to be a solid, one of them tends to be a gas, totally different colors, and then we mix them together to form something that doesn't have any properties in common with either of them. It is white in color. It happens to be very tasty and not toxic. It is also not soft. And it's a powder. So it's a solid, which is the only similarity to sodium that we can really see. So just a reminder that when you form compounds, those properties are very different than the properties of the elements. So these properties of ionic compound are similar to other ionic compounds, and these are a result of the features of ionic bonding and how strong it is. Results of the strength of an ionic bond. An ionic bond is one of the strongest bonds that you can make. And it's because of how the electrons are shared, or rather not actually shared. So let's look again at sodium and chlorine. Let's write the electron configuration for those two. So sodium is over here. It's in the third row and it's in the S block. So the 3s1 is its valence electron, and the noble gas that comes before it is the second row neon. So its configuration of the neutral sodium is neon 3s1. And for chlorine, I think we can find it here in the third row. It is in the 3p block, so it has 2 3s electrons, and it has 1, 2, 3, 4, 5 3p electrons past its most recent noble gas, which was neon. We can write neon 3s2 3p5. So the only electrons we can see for both of these are the valence electrons, which are the ones available for bonding. And remember when we said on the previous slide, the way we can predict what kind of atom, which kind of ion, a cation or an anion that something is going to form, is by looking at how, the easiest way to get to a noble gas configuration. So the lowest energy orientation is the same configuration as a noble gas. So each atom will react to try and reach a noble gas configuration in the easiest possible way. And so sodium, to reach a noble gas configuration, all it has to do is lose 1 valence electron, and then it will look like neon. And chlorine would have to lose 5 to reach neon, but it only needs to gain 1 to reach the next noble gas, which would be argon. And we're not just talking about giving and taking theoretically, we are literally talking about chlorine taking that electron from sodium. So sodium is giving and chlorine is taking that electron. And that's how the ions are formed. So we form sodium plus, we lose that valence electron, and now it has the same configuration as neon. And we formed chlorine minus, called chloride, by adding an electron to make 3s2 3p6, which is the same configuration as argon, the next noble gas. And I want to take time to write down those words we use to describe the transfer. So sodium, we say that it gives its valence electron to chlorine. And we say that chlorine takes a valence electron, the valence electron, from sodium. And I don't know about you, but when I start to use words like giving and taking, I do not think this counts as sharing. These are not words I would use to describe sharing. And I would like to emphasize that here, because the next type of bonding we'll talk about does involve sharing. So ionic bonding most definitely is not sharing. And so after this giving and taking, we have ions that are formed, a cation with a positive charge and an anion with a negative charge. And these ions are attracted to each other. And that's why ionic bonds form. The ions formed are attracted to each other. Remember from when we talked about the experiments leading to the discovery of the subatomic particles, that opposite charges attract and like charges repel. So positive attracts negative. This is officially called electrostatic attraction. So this electrostatic attraction is very, very strong. There is nothing stronger than a negatively charged thing attracting a positively charged thing. And so the strength of this electrostatic attraction between positive and negative is the reason for all these unique properties of ionic compounds. That extra high strength of the bond means that the high melting point and the boiling point are very high, because a lot of energy is required to break that incredibly strong bond. It's also the reason that the compound is crystalline and brittle, because of that repeating pattern and that easy ability to shatter. The conductivity in water is due to the fact that ions contain charged ions, and in water, when they become ions once again, and they're free, they can trade electrons back and forth. So that is the basics of ionic compounds, ionic bonding, and how ions are formed. The next thing we'll talk about will be the other type of bonding, which is covalent bonding.